So we now have an algorithm for finding the maximum parsimony tree for any given data set. We built the list of all possible trees. For each tree, we then use the Fitch algorithm to determine its length, and then we finally pick the best among all these possible trees. There's just one problem with that, and that is that tree space, the space of all possible trees, is incredibly huge. It grows tremendously rapidly. Let me just walk you through how incredibly rapidly this tree space grows with the number of species. To do that, we first need to start thinking about the relationship between the number of species and the number of branches on a tree. A simple way of coming up with an equation for that is to think about it inductively. So if we start out with a tree with 3 species, there's just one way of making such a tree. This has 3 species and 3 branches. You can see that if we add a 4th species to this tree, like I've done at the bottom of the slide here, then I'm actually adding 2 new branches. So where we before had 3 branches, we now have 5. This is true every time I add an extra species. Every time I add an extra species, I will add 2 more branches. This means that the total number of branches, if you have X tips, will be 3 from the original tree, and then it will be 2 for each additional branch, meaning each additional branch in addition to the original, each additional species, in addition to the original 3. So the total number of branches will be 3 from the original, plus 2 times the number of species that are in excess of 3. So 3 plus x minus 3 times 2. Multiply it out, it's 3 plus 2x minus 6. Rearrange a bit, we get 2x minus 3. So if we have x tips, then we have 2x minus 3 branches. If we have 10 species, for instance, then we have 2 times 10, that's 20 minus 3, then that's 17 branches. It's a very simple relationship. And we're going to use that now. Because how many unrooted trees are there? It turns out we can derive an equation for that based on our knowledge about the number of branches for a given number of species. As I said, if you have x tips, then you have 2x minus 3 branches. As you saw before when we wrote up the algorithm, when I illustrated the algorithm for building the set of all possible trees, we can build all possible trees by gradually adding 1 species at a time. Combining these 2 will tell us how many possible trees there are. The original tree here has 3 branches. For each of these 3 branches, we can add the 4th species. Since in general a tree with x tips have 2x minus 3 branches, it means that from a tree with x tips we can make 2x minus 3 derived trees, which each have 1 additional tip. And this actually forms the basis of the equation for telling us how many possible trees there are. We start out with I equals 2, then for each tree we can see there are 2i minus 3 branches on that tree, corresponding to 2i minus 3 derived trees. This will give us a tree with 1 more tip. This will then have 2i minus 3 derived trees. I increases 1. This will then have 2i minus 3, and we have to multiply these numbers. If we look at an example, start out with 3 species. There's 1 tree. This tree has 3 branches, corresponding to us being able to make 3 derived trees. So from the 1 original tree, we can make 3 trees with 4 tips. A 4-tipped tree, using our formula, turns out to have 5 branches, meaning we can make 5 derived trees. So there are 1 times 3 times 5, 15 trees with 5 tips. A 5-tipped tree, according to our formula, has 7 branches, meaning we can make 7 derived trees from each of our 15 original trees here, meaning we now have a total of 15 times 7 trees with 6 tips. 6-tipped tree has 9 branches, etc., etc. You can see the formula, 1 times 3 times 5 times 7 times 9 times 11, etc., etc., tells us how many trees there are with any given number of tips. This is captured in this formula. You can see that this is a number that increases incredibly rapidly. Already we have 1 tree with 3 species, 3 with 4, 100 with 6 species. With 10 species, we're above 2 million. With 13 species, we're above 13 billion, and it just keeps rising. And this is problematic. This actually means that it's not possible to do an exhaustive search of tree space for larger data sets. With the computers and the storage capacity we have today, we can probably go to around 12, 13 species and do an exhaustive search. Above that, it would simply take too much time to look through all of these trees. For each of them, use the Fitch algorithm, store the number, and go back and find the smallest tree. So that's a bit of a problem, and it's a problem we always run into in bioinformatics. We have problems that are exploding because of the combinatorics, and that means that exhaustive searches are typically not possible. So our original algorithm, our original approach for finding a maximum parsimony tree will not work because of this, or at least it will only work up to some limited size, but we would like to have larger data sets than this. How do we solve that? There are two ways of doing this. One, which is a solution for sort of a medium range of dataset sizes, is called branch and bound. The idea in branch and bound is that you have some bound, you have some limit on, you have a previous knowledge before you start trying to find the best tree. You have previous knowledge, a bound on how good you are at least able to do it. This is the bound. So in trying to reconstruct a parsimony tree, for instance, one way to setting a bound is to just randomly construct a tree, use Fitch to compute the length on that particular random tree, and this is now your bound. So if we have 5 species, for instance, we might randomly construct a tree like this and use Fitch to determine that this tree has a length of 798 mutations on some data set we're looking at. Okay, what's the idea in branch and bound then? Well, in branch and bound, we try to gradually build the tree using this one at a time species addition outline I just showed you before. But what we then try to do is we try to use the bound to cut off lineages of this tree construction that appear not to be working for us. So in this case, with the bound that we had here, let's see here. We start with a tree with 3 species. There are 3 possible derived trees from that. We can place the 4th species on the A, the B, or the C branch. Let's assume we now place the 4th species on the A branch and then use Fitch on this unfinished tree. This unfinished tree, it turns out, has a length of 978. Okay? That's larger than our bound of 798. We now know that this tree, if we add the 5th species, this will always lead to a worse tree. We will always need more mutations when we add more species. So we know that since this tree that's part on the way to the finish line, since this is already worse than a bound we have, we know we don't need to look any further. We don't need to add the 5th species on all the possible branches of this tree. So we cut off this lineage, we don't look at it any further. Similarly, if we place the D on the C branch, do Fitch on that, it turns out that that has a length of 856. That's larger than our initial bound of 798. So we now ditch this lineage, we don't explore this any further. The central T, we put the D on it. Let's say it has a length of 500. I forgot to put that on the slide. It has a length of 500. That's better than our bound, so we continue along these lines. Okay? So starting with the middle tree here, we now have 5 possible derived trees where we can add the E. We can add it to the A, B, C, D branch and to the internal branch. This gives us 5 trees. For each of them, we look at their length. This one is the same as the one we randomly constructed at the beginning. It has the same length as our initial bound. Second one has a length that's worse than the bound. Third one has a length that's better. 4th one has a length that's worse, and the 5th one also has a length that's worse. So in this way, we found this tree to be the best. Branch and bound in this way is guaranteed to find the best tree. It looks through all of tree space without actually doing it because it can cut off entire sub-regions of tree space where it doesn't have to go. This means that it's much more efficient than a heuristic search, although this will depend on your actual data. Worst case, branch and bound might still have to look through all of tree space, but typically it increases it a bit so we can push the limit with a couple of extra species. In the cases where branch and bound does not work, and that is quite often, that's for any realistic sized data set, I'd say, we instead have to use a heuristic approach. Heuristic means rule of thumb. It's a method that seems to work nicely, but where there's no guarantee that you will find the best solution. Heuristic searching of tree space And this is actually something that is used not just for parsimony, but also for distance-based and maximum likelihood methods. Heuristic search is done in the following manner. We start by constructing some initial tree. Could be a random tree where we just sequentially add the species. For this particular tree, we can determine its length using the Fitch algorithm. Starting with our initial tree, we now make a set of neighboring trees, meaning we take the initial tree, then we move species around a bit, we swap branches and do other small rearrangements of that type. For each of these neighboring trees, we can determine the length. If any of the neighboring trees are better than the original tree, then we can select it and use that as a new starting point for a new round of rearrangements. Okay, so we start with a subtree, make a set of neighbors, find one that's better, pick that one, make a set of neighbors to that, pick the best one, and keep going like that. We keep going like that until we find a tree that's better than all of its neighbors. And at this point, we found a local optimum. It's not necessarily a global optimum. We've climbed, as it were, to the top of a hill. And this is an example of a very general algorithm in engineering where we optimize something by gradually changing parameters until we find an optimum. It's possible that there is a higher hill somewhere else. We don't know that. But if we start in, say, 10 different places and always end up on the same tree, then probably we're doing okay. At the end, let me just mention the 3 typical types of rearrangement we use to do these searches of tree space, because you will run into these in the exercises and also in the literature. Rearrangement type number 1, nearest neighbor interchange, INNI, is the simplest of all rearrangement types. You start out with a tree. In this case, the numbers 1, 2, 3, and 4 should each be thought of as being entire subtrees. You have several species in each of the 4 subtrees here. The idea in nearest neighbor interchange is simply that you start out for each internal branch in the tree, you swap 2 of these groups. So on this tree, we've swapped groups 2 and 3. So now 1 is together with 3. At first, it was together with 2. On the other tree down here, you swapped 4 and 2. So 1 is now together with 4 instead of being together with 2. In nearest neighbor interchange, you do this for every internal branch in the tree. So for every internal branch, you have 2 neighbors. This means that, for instance, a tree with 20 tips will have 34 neighbors. Rearrangement type number 2, subtree pruning and regrafting. The idea is you start out with a tree, you cut off a subtree. This subtree, you then use the cut point to insert on every possible branch in the other tree. Okay? So this will give you a range of neighbors for this particular cut point. You do that for every possible cut point in the tree. You can see that this will give you a larger set of rearrangements for every possible cut point. So subtree pruning and regrafting, INNI is a subset of that. You will get more possible tree rearrangements using this. Final type of rearrangement, tree bisection and reconnection, TBR. Start as before, we divide the tree into 2 subtrees. But now, instead of using the cut point to insert on every branch in the other, we now use every branch in one subtree to insert on every branch in the other subtree. So again, you can see this is a larger set of rearrangements, and both INNI and SPR are in fact subsets of TBR. These are the methods used when we're doing heuristic searching of tree space. This is typically something you can set in software and say, I want to do a TBR search of tree space, that's a more thorough search, or I can do an INNI, that's a less thorough, but maybe more rapid search of tree space.